In this video on indices and logarithms, we'll be talking about solving logarithmic models. So what kind of models do we have in real life that can be seen as logarithmic models? We already saw indicial models, or what you can call exponential models, in areas like growth. We saw growth and decay. Then we also saw think compound interest, which is basically still like growth and decay like that too. So let's look at models in real life that can be considered to be logarithmic in nature. Okay, so the first question is, what is a logarithmic model? So a logarithmic model is an equation in which the variable appears inside a logarithm, right? The variable we are looking for appears inside a logarithm. So just like that, that's what we have for a logarithmic equation too. The variable we are looking for appears inside the log. All right. So the general form is y equals a plus b log x to base c. That's the general form, where a here is the vertical shift. So this shifts the function vertically. B is the stretch or compression factor. So this B now either compresses or expands the graph. Then C is the base of the logarithm. Of course, we've been dealing with base forever. And then X is the value which must be greater than 0, because you cannot take the logarithm of a negative number. It will be undefined. So the logarithm, any number whose log you want to take, must be greater than 0. It must be positive. Of course, we know for the base has got to be not equal to the base has got to be greater than 0 and not 1. It can be anything between 0 and 1 and anything above 1. Then we have logarithmic models are commonly used in earthquake measurement, sound intensity, acidity when we talk about pH scale, then population growth, and even in finance. Okay, so we go on to look at some laws of logarithm just to refresh our minds about this. First, we have the product, which tells us that the log of m multiplied by n to base b is the same thing as log m to base b plus log n to base b. On the other hand, if you also have log m to base b plus log n to base b, it also can be written as log m times n to base b. Then we have the quotient rule, which tells us that the log of m divided by n to base b is the same thing as log m to base b minus log n to base b. So if you also have this, you can go take it back to the quotient. Then we have power rule, which says that log m raised by k to base b is the same thing as k log m to base b. And then we also have the inverse property, knowing that exponents are inverses of logarithms. So log x to base b equals y simply means that b raised power y is equal to x. So these are some very important laws of logarithm we need to pay attention to. Of course, there are some other laws that log b base b is equal to 1. Log 1 base anything is equal to 0, because anything raised power 0 is 1. So and we also have like maybe fractional basis and power basis like that. So like that. Then we have how to solve basic logarithmic equations, which we'll be doing, of course, before. This is just a refresher. So solve log x to base 3 equals 4. So convert to exponential mode, of course, this has to be 3 raised by 4 equals that means x is 81. So the solution is 81 straight up. Of course, we know that x has got to be positive and its 1 is positive, so no worries. Then we have example 2 now, where we solve log 2x minus 1 to base 5 equals 3. So if you look at the domain restriction, 2x minus 1 should be greater than 0, meaning that x should be greater than half, right? So anything we get that is uh that is less than, if you get anything less than half as answer, that it won't work. But if it's greater than half, then we are good to go. So what do? We write this log as exponent. So we have 5 raised power 3 equals 2x minus 1. That's 125 equals 2x minus 1. That means we have 125 plus 1, which is 126, 2x. So divide 3 by 2, we have x is 63. And since, of course, where the domain check is just coming here, so x is greater than half, just like we already did. And then since 63 is greater than half, then the solution is valid, because 63 is greater than half. Now, what else? Solving equations with multiple logarithms. So if you have problems with multiple logarithms, we've encountered all of this in previous videos already, right? So you want to solve log x to base 2 plus log x to base 2 plus log x minus 3 to base 2 equals 3. So like I always advise, do the domain restriction first. X should be positive, that's x should be greater than 0, and x minus 3 should be greater than 0, which means x should be greater than 3. And if x is greater than 3, it automatically means it is greater than 0. So the stronger restriction is that x should be greater than 3. So once that is settled, of course, I know that comes later here, but for me, I like to do the domain restriction first because from the domain restriction, you can always decide if the solution, if you're going to have a solution or not. Okay, you can then use product rule. Now that you know, you can then use the product rule, right? Where you have log base 2 of x into x minus 3 equals 3, and then you can write the next. You can expand that as x times x squared minus 3x. Then 2 raised power 3, you can then have that. So you have 2 raised power 3 equals x squared minus 3x. That means 2 raised power 3, 8 is equal to x squared minus 3x. Then you can form a quadratic expression, which is now x squared minus 3x minus 8. If you transfer the 8 equals 0. So you can then factor that to be x minus 4 into x plus 2 equals 0. Okay? X minus 4 into x plus 2 equals 0. And then you have x equals 4, x equals minus 3. I have doubts about this. Seriously, this is x squared minus 3x minus 8. X squared minus 3x minus 8 equals 0. We need two numbers to multiply. I don't think this works though. Yeah, and something is definitely wrong with this. It's not looking correct. Okay, let me just use Wolfram Alpha straight up and see what happens. X squared minus, because if we expand it, that's x squared minus 4x plus 2x. This will be minus 2x. It doesn't work. Yeah, something is wrong here. So, or let me even solve using formula. There's no point even trying to do that. Something that factorization is not working. Okay, let's just do this. I'll just go straight. I know x is equal to minus b. B is minus 3. That's plus 3 plus or minus square root of minus b again. That's minus 3 squared. That's 9. Minus 4 times 1 times minus 4 times 1 times minus 8. That's plus 32 right there. Plus 3, 2, all over 2 times 1, that's 2. Okay, so we have x to be 3 plus or minus square root of 41 all over 2. Yeah, so that is not correct. Just so 3 plus or minus root 41. Okay, so this should actually be 3. So here we can't even fact. Yeah, the factor is not so straightforward like that. So what we should be having here should be this. So no factoring. We can just get the values of x, right? We know we got 3 plus or minus root 41 over 2. Okay, 3 plus or minus root 41 over 2. So that's frac, right? Mm, okay, that'll be d frac 3 plus or minus root SQRT of 41 all over 2. Okay, so okay, I can just copy and paste this now. So I can have this 2. So I have this. So I can have this first of all here. And then next I can just have, so this one can be minus, and this one will now be same expression now. And this one will be plus. So this is plus. So let's see what that looks like first. Then I'll go and take the decimal part of it. So this is more like what we should have here. So it was wrong to have said, to have been able to factorize that. So that's minus b, that's 3 plus or minus square root of b squared minus 4 times 1, 4, minus times 8. That's 9 plus 32, which is 41. So we have this. So let me even get the approximate results. 3 minus root 41. 3 minus square root of 41 divided by, okay, divided by 2. That's minus 1.7015. For this now, we have plus, so this plus now. We have 4.7015. Okay, so 4.7015 there. So this is approximately minus 1.4015, right? Minus 1.7015. On the other hand, this one is approximately 4.7015. Okay, actually 6. 4.7016. This one too is 6. Okay, so I think we have that now. So we have this. Now, original restrictions. Now, x should be greater than 0, and x minus 3 should be greater than 0. That means x is greater than 3. So the valid solution will not be the first one. The only valid solution is this one now. The valid solution is the second one, which is this. So the only valid solution we have is this one now. So this is the only valid solution. 3 points root 41. Okay, x equals all that, right? So the only valid solution is x, which is equal to x, which is approximately this. And of course, because it's greater than 3. So that's the only one that meets the criteria of x, or the criterion of x being greater than 3. So that's all we have there. Okay, I have this to approximate twice, so I can get rid of that. Yeah, so that's it. So for that example, we have all that. Now, let's talk about some, the reason why we're here is to solve logarithmic models. So real world logarithmic models. Now that's what we're going to see in this next section. So the earthquake magnitude model, for instance, is a logarithmic model because the Richter scale formula is given as m equals log to base 10 of I over I naught, where m is the magnitude. When an earthquake happens, and that happens a lot in my location in Japan in general, there's a lot of earthquake going on. So the intensity, the magnitude of the earthquake on the Richter scale determines how intense, how serious or devastating the earthquake can be. So you have m equals log to base 10 of 1 I over I naught, where m is magnitude, I is intensity, and I naught is the reference intensity. So we have a problem in that line, and this is it. An earthquake measures 6. That means m is 6. How many times stronger is it than the magnitude 4 earthquake? So how much stronger is a magnitude 6 earthquake compared to a magnitude 4 earthquake? So you write the equations now. M is equal to log 10 I1 to I naught. So I is the intensity which we want to measure now. So we have 4 log to base 10 of I2 over I naught. Okay. Okay. This is like, yes. So we have the one of 6 and we have the one of 4. So if we want to convert to exponential form, then we know that this is based on the law of logarithm. This is 10 raised power 6 equals I over I naught. And this one is 10 raised power 4 equals, so the I1 and I2 are not the same, right? So we are interested in these intensities. So we have 10 raised power 6 equals I1 over I naught, 10 raised power 4 equals I2 over I naught. So what do we now do? We compare. So we have, so we want to find how stronger is I1 to I2. So we have I1, I2. I1, if you make I1 the subject here, that'll be 10 raised power 6 I naught. I2 is 10 raised power 6, 10 raised power 4 I naught. So I1 divided by I2 will just be 10 raised power 6 I naught divided by 10 raised power 4 I naught. And the I naught can cancel out, so you just have 10 raised power 6 over 10 raised power 4, which is 10 raised power 2, and that is 100. So we can then say that a magnitude 6 earthquake is 100 times stronger than a magnitude 4 earthquake. Okay? So based on the formulas, so that's how the earthquake thing goes. Then we have sound intensity model in decibels. It goes around it takes up the same structure of the earthquake model, where we have D equals 10 Oh, okay. We have 10 now. We have a kind of stretching or compression factor for the decibel, and that's what how sounds good. That's why sounds can be strong or not strong. So you have D to be equal to 10, log to base 10 of 1 over I over I naught rather. So we have a sound measures 90 decibel. Find the intensity ratio. So we have the decibel to be 90. We have 10 here, log to base 10 of I over I naught. So we need I over I naught. That's the intensity ratio now. So what we can do here is to divide both sides by 10. So we have 90 divided by 10. We have 9. 10 cancels out here because we've divided. So we have log to base 10 of I over 10. And because we are interested in the intensity ratio, we need I naught, I over I naught. So that would just be 10 raised to power 9. So 10 carries 9 on its head. We turn it to exponents. So I over I naught is 10 raised to power 9. And that is 1 billion, right? So we say the sound intensity is 1 billion times the reference intensity. Whatever the reference intensity is, the sound of 90 decibel is 1 billion times the reference intensity. So that's talking about sound intensity model. So we see logarithmic models for earthquake model, sound intensity, and of course we have pH model too. So imagine for pH, that's pH to measures the level of acidity of a chemical or some of a solution. Maybe we should put it as solution. So we have a pH model like this. So pH is equal to minus log to base 10 of H plus. I think I did this in chemistry, in year one chemistry or in high school chemistry. So the problem is find hydrogen ion concentration if the pH is 3. So the hydrogen ion concentration is this H plus we have here. So the pH is 3, right? So of course a pH of 3 shows some level of acidity, I believe. So I think pH of 7 is neutral or something like that. So we have 3 to be minus log to base 10 of H plus. So we want to get rid of the minus, so we take the minus away, multiply by minus 1. So we have minus 3 equals log to base 10 of H plus, and then convert to exponential form. So it means this 10 we just carry 3 on it. So we have 10 raised to the power minus 3 equals the concentration of H plus. That means the concentration of H plus is 10 raised to the power minus 3, which is 1 over 1000. That's 1 over 10 raised to the power 3, which is 1 over 1000, which is 0.001, like that. So that's the concentration of hydrogen ion if you have a pH of 3. Okay. Now, solving logarithmic model for the variable. So imagine you have P equals 5,000 log T to base 10 plus 20,000. So you want to find T when P is 25,000. So all you just need to do is put P as 25,000 equals 5,000 log T to base 10 plus 20,000. So you can subtract 20,000 from both sides. So you have 25,000 minus 20,000, that's 5,000 equals 5,000 log T to base 10. 20,000 has disappeared because you subtracted already. So the next thing, you can divide both sides by 5,000. So 5,000 divided by 5 on both sides, you have 1 equals log T to base 10. Now, all we need is T. So T cannot be isolated by just saying T raised power 1. So T raised power 1 is equal to T. And then that means T is equal to 10. In this case, when P is 25,000, like that. So in all, we see the strategy for solving logarithmic models here. You isolate the logarithm for the most part, and then apply logarithm laws if needed, then convert to exponential form and solve algebraically and check domain restrictions if necessary. Okay, so we have some practice problems. As usual, I'll take two, and I'll take two. I'll take solve one from 1 to 10 and another one from 11 to 20, and we'll call it a day. So, what should I do now? Let me see. Let me see. Which one is really challenging here? Which one looks challenging? Uh, Maybe really none. So just take any random one and just walk away with it. Um, okay. I think question 8, maybe. Question 8. So log x base 3 plus log x minus x base 3 equals 4, right? Log x base 3 log x base 3 plus log x minus 8 base 3 equals 4. Final check to be sure. Log x base 3 plus log x minus 8 base 3 equals 4. Okay. So, the first thing we want to do here is, okay, for me, like I like to talk about the domain restrictions first. Domain restrictions, because that can already tell you if there's an answer or not. So for domain restrictions, we have this one, x should be greater than 0, settled. Then x minus 8 should be greater than 0 too. So x is greater than 8. That's the requirement. Overall, if x is greater than 8, it's automatically greater than 0. So we have x greater than 8. Okay, so we have that. Then we can go ahead and solve, right? So we can apply logarithm laws. So we have log x to base 3 plus log x minus 8 to base 3 equals 4. And then applying laws of logarithm, applying product law, for instance, applying the product law of logarithm, right? So sum outside logarithm becomes product. So that means if we have this, then we can multiply x and x minus 8. Okay, so we have log, okay, we have now log to base 3, log to base 3 of x into x minus 8 equals 4. Okay, then the next thing is we convert to exponent, convert to indicial or exponential form, if you like. Convert to indicial form. So what do we have then? 3 carries 4 on its head, like I like to say. So we have x into x minus 8 equals 3 raised to power 4. So that means we have x squared minus 8x equals 81. All right. So that means x squared minus 8x minus 81 is equal to 0. So we have this to grapple with now. Okay, so with that in place, we know that here A is equal to 1, B is equal to minus 8, and C is equal to minus 81. It's like we're in for some big values. Or, well, yeah, I mean, this is still quadratic, so we can still flex our muscles a little bit here. So X is equal to okay, well, the formula, if you don't remember, it's minus B plus or minus square root. That's the quadratic formula, which some people call almighty formula. I really wonder what is almighty about this. When they are still, when we have Maxwell and Schrodinger equations in physics. So we have minus b, that's minus 8, plus or minus square root of minus 8 squared minus 4 into 1 into minus 81, right? Yeah, 4ac all over 2 times 1. Okay, so x now is equal to 8 plus or minus square root of 64 plus 81 times 4, that is 324, I believe. 324. Oh, 8 squared is 64, yeah? Then this is 4 times 1, 4, 4 times, that's 324 divided by 2. And that is x equals 8 plus or minus square root of 64 plus 324, that's 388, I think. 388. Yes, 388 all over 2. So we need to break this down to see if there's a what is it called now? A perfect square. So we have 388 divided by 2. That's 194. Yeah. 2 again, that's 97. And that's how far that goes. So in this case now we have still 388 is 4 times 97. Yeah, 4 times 97. 4 times 728. 4 times 936. That's 388. So that's 4 times 97 in short. So we have x to be equal to 8 plus or minus 4 times 97 divided by 2. Okay, so we have x to be equal to 8 plus or minus 2 root 97 all over 2. So that means x alone now, x is 8 plus or minus root 97 because we've divided by 2 already. So it means we have x is equal to 8 minus root 97, which is clearly not greater than 8 that we are talking about, because by the time we subtract this now, oh, but should I be too sure about that? Yeah, this is going to be 8 point something. This is negative for sure. So it's not greater than 8. So we have that. Then we also have x equals 8 plus root 97. Maybe I should bring that down. Okay. Or x is equal to 8 plus root 97, which is clearly greater than 8. I think that's the domain restriction, right? It's clear. The domain restriction says x should be greater than 8. So yeah, it should be greater than 8. So this one is clearly greater than 8 because we already have 8 here. All right. If you add something to it, it becomes more than 8. But this one is less than 8. So we can conclude. So the valid answer the valid answer is x is equal to 8 plus roots 97. Okay, you can also punch your calculator to get it in decimal form, but I think this is sufficient. Okay, so that's question from the first 11, from the first 10 rather. From the second 10, okay, we've solved questions on earthquake model, on if earthquake magnitude increases from 4 to 6, how much stronger is it? We've done something like that. The sound intensity, we've done something like that. pH, we've done something like this. Uh, Solve logarithmic equations requiring log laws. Okay, we have done things like this too. So I may have to go back to a pH question, or to one of those other questions. Yeah. Question 14 says, if a sound increases from 60 decibel to 80 decibel, how many times greater is the intensity? Okay, so a sound increases from 60 decibel to 80 decibel. So I think I want to do that. Uh, Again, the sound intensity formula is D equals 10 log to base 10 I over I10, right? So you have a sound increasing. So I'm taking question 14 now. So let me do my normal snipping. Question 14. Question 14. Then I copy and take it to the page over there, to the worksheet, like I like to say. Okay, I need to paste like this. Okay, so if a sound increases from 60 decibel to 80 decibel, so we have sound one, that's 60 decibel, then sound two is 80 decibel. So how many times greater is the intensity? Okay, so and we know the model is this, that decibel is equal to 10 10 log to base 10 of intensity over base intensity, right? So in this case now, um we need the first intensity D1. D1 is such that we have 60, equals 10 log to base 10 into I1, that's the first intensity over the benchmark intensity, the basic intensity. So from there, what do we have? We can divide both sides by 10. So we have 60 over 10 equals 10 over 10 log to base 10 into I1 all over I10. Okay, so this goes, and we have 6 here equals log to base 10 into I1 over I10, over I naught, right? So in this case now, this 10 can carry 6 on its head. So we have I1 over I naught equals 10 raised to power 6. That means that I1 is equal to 10 raised to power 6 multiplied by I naught. So we can keep this now, okay? That's the initial 60 decibel sound. So because we want to look how many times greater is the intensity. So we got that. Then we do the same thing for the second one, where we then have so for D2 now, D2 is a 80 decibel sound. So we have 80 equals 10 log to base 10 of intensity 2 all over the initial intensity, the reference intensity. So divide through by 10 again. So we have 8 is equal to log to base 10 of I2 over I naught. Okay. And from here, we can isolate I2 over I naught. So we have 8 raised to power 10. I mean 10 raised to power 8 now. 10 raised to power 8. So this was 10 raised to power 6. 10 raised to power 8 equals I2 over I naught. So again, we have I2 to be uh 10 raised power 8 I naught. So we have that too. So the question we are answering is how many times greater is the intensity? So um so let me say comparative intensity, just allow me use that word. Comparative intensity can then be said to be intensity can be given as, okay, that will now be I2 over I1. All right. We know I2 is 10 raised power 8 I naught, and I1 is 10 raised power 6 I naught. So this is 10 raised power 8 I naught, and this is 10 raised power 6 I naught. So I naught cancels I naught. So we have 10 raised power 8 all over 10 raised. Okay, let me bring it down so I can keep having enough space. So that's 10 raised power 8 over 10 raised power 6. It's all the I naughts gone. So, and that is 10 raised power 8 minus 6. So that is 10 raised power 2. And 10 raised power 2 is simply 100. Okay. So what's the answer now? That we need how many times greater is the intensity? So, uh, so the intensity, the intensity is 100 times greater. It's 100 times greater. Okay. The intensity is 100 times greater if a sound eh, greater if a sound increases from 60 decibel to 80 decibel. So from 60 to 80 decibel. So with that, we have that in the bag. So we have that taken care of. So be sure to try all the questions. This 1 to 10, and then we have the rest. Okay, these ones are too much to show at once. So you have 1 to 10, then you have 11 to 16 here, talking about some real world applications, and then you have 17 to 20 here. Okay, so let me know how helpful this is for you, and if there's something else you'd like me to try out, feel very free to let me know. If you have subscribed already, I must thank you very much for doing that. If you haven't subscribed, go ahead please and subscribe and hit the notification bell so you can always get alerted each time a new video is released. Having done that, you can also become a member of the channel by clicking on join. That comes with special privileges like you seeing some videos alone, or you see the videos first before others see them. You can request for PDF copies of my notes. You can actually hang out with me to talk about anything that interests you on my channel. Ultimately, don't forget to comment, like, and share so that more people can have access to the great content I have going on here. Till I come your way again, keep doing math right. Bye.